There is a mark on the surface of the moon, about 2,000 miles from where you are right now, give or take. It is roughly 4 meters long, a smear of pale dust surrounded by a faint halo ending at a small dark crater no wider than your living room. It was not there in 2016. NASA's Lunar Reconnaissance Orbiter took a photograph of it 11 days after it appeared. The angle of the smear runs roughly north to south. From the geometry of the spray pattern, planetary scientists could reconstruct what happened. Whatever made that mark had been moving sideways, almost horizontally, at something close to 1 kilometer per second. That mark is going to be there for a very long time. There is no wind on the moon. There is no water. There are no plate tectonics, no erosion, no seasons, no weather of any kind. Over the next few million years, the slow drizzle of micrometeorite impacts will gradually smooth it out, the way a beach is smoothed by waves. But that takes geological time. In human terms, it might as well be permanent. That smear is the grave of a spacecraft called Beresheet, pronounced Beresheet. The name comes from the first word of the Hebrew Bible. In English, it is usually translated as "in the beginning." And on the night it died, Beresheet was 14 minutes away from making its country the fourth in human history to land something on the surface of the moon. After the United States, the Soviet Union, and the People's Republic of China, it was also by a wide margin the smallest lunar lander ever attempted. The cheapest, the youngest. Beresheet was about the size of a washing machine. Fully fueled, it weighed less than the average grand piano. It had been built by a non-profit. Its 3 founders had hatched the idea at a bar in Holon, a suburb of Tel Aviv, when they were in their mid-20s. The total budget of the project was $100 million. To put that in context, the Apollo program, adjusted for inflation, spent that much money roughly every 6 hours. Beresheet was not supposed to win. It was not supposed to even reach the moon. Every space agency professional who looked at the Space IL team in the early years told them politely but firmly that what they were proposing was impossible on the budget they had. They were wrong. Space IL did reach the moon. They achieved lunar orbit insertion on April 4, 2019. This made Israel the 7th nation on Earth to slip a spacecraft into orbit around our nearest neighbor. By any reasonable metric, this alone was a triumph. A 50-person volunteer outfit run out of a building southeast of Tel Aviv had pulled off something only 6 other nations had ever managed. But that is not what this story is about. This story is about the next 7 days. It is about what happened between the moment Beresheet achieved lunar orbit and the moment exactly 1 week later when its telemetry froze. Frozen on a screen at 149 meters of altitude. Horizontal velocity 946.7 meters per second. Vertical velocity 134.3 meters per second. It is about what happened in the 14 minutes between the moment its main engine ignited for the final descent burn and the moment a 4-meter smear appeared in the Mare Serenitatis. At its heart, this is a story about a single command, a single line of software sent up from the surface of one world to the immediate vicinity of another by a group of engineers in a panic. A command which, due to a quirk in how the spacecraft had been wired together, triggered a cascade of consequences. Consequences nobody had simulated. Nobody had wargamed. Nobody in the moment fully understood until it was too late to do anything about it. It is also a story about money. Specifically about what you have to sacrifice when you try to build a moonlander for 200 times less than the next cheapest one ever made. About which corners are safe to cut. About which ones in hindsight were not. To understand how a small Israeli nonprofit got within 149 meters of the lunar surface, and then in the space of about 90 seconds lost everything, we need to go back. Not just to 2019. Not just to the launch in February. We need to go all the way back to 2007. To a competition that by the time Beresheet finally reached the moon no longer technically existed. To a $20 million prize that was never actually paid out. And to a question. A very simple question posted on Facebook in 2010 by a 24-year-old electrical engineer. The question was this: who wants to go to the moon? In September 2007, a fairly unusual thing happened in the world of space exploration. A private company, Google, announced that it would give $20 million to whichever private team anywhere in the world could be the first to land a robotic spacecraft on the moon. The spacecraft had to travel at least 500 meters across the surface once it got there. It had to send back high-definition video. And it had to do all of this with less than 10% government funding. This was on its face a deeply strange offer. The list of organizations that had ever successfully landed something on the moon in the half-century since Apollo 11 was extraordinarily short. The United States, the Soviet Union. That was it. No private company had ever even attempted it. The reason was not mystery or hubris or lack of will. The reason was money. Landing on the moon was, by the standards of any sensible commercial enterprise, an absurd thing to spend money on. It cost billions. It produced no revenue. The customers, to the extent that anyone could be considered a customer of a lunar lander, were governments and research institutions, and they were perfectly capable of building their own. Nevertheless, by 2008, 29 teams from around the world had registered for the Google Lunar X Prize. They came from every continent except Antarctica. There was Astrobotic, a spin-off from Carnegie Mellon University in Pittsburgh. There was Moon Express, founded by a group of Silicon Valley entrepreneurs who genuinely believed they could mine helium-3 from the lunar regolith and sell it as fusion fuel. There was Team Indus from India, Synergy Moon from a coalition of 15 countries, PT scientists from Germany, Hakuto from Japan, and Space Maida from Brazil. There was also, almost as an afterthought, a tiny Israeli team that did not yet have a name or an office or really anything beyond a Facebook post. And 3 20-something engineers who had recently graduated from Ben Gurion University of the Negev. Most of the early teams were serious. Most had funding, or at least the credible promise of funding. Most had aerospace veterans on staff or access to existing satellite hardware they could modify. The deadline when the prize was first announced was December 31st, 2012. That was nominally 5 years to design, build, launch, and land a spacecraft on the moon. For perspective, the Apollo program, with unlimited funding and the urgent strategic motivation of the Cold War, took 8 years from start to first lunar landing. The Surveyor program, NASA's robotic precursor to Apollo, took 5. The deadline slipped. In 2010, it was pushed to 2014. In 2014 to 2015. In 2015 to 2016. In 2016 to 2017. By 2017, only 5 teams remained as finalists. Google had begun to quietly suggest through proxies that they were not optimistic any of them would actually make the launch window. The remaining 5 were SpaceX, Moon Express, Synergy Moon, Team Indus, and Hakuto. By the new and final 2018 deadline, 4 of those 5 were still in serious technical difficulty. SpaceX had what they described as a launch contract, a paid-up ride on a SpaceX Falcon 9, and a spacecraft in some stage of advanced assembly. Moon Express was not yet ready. Team Indus had been forced to halt work for funding reasons. Synergy Moon was unable to confirm a launch provider. Hakuto, the Japanese team, had withdrawn entirely. On January 23, 2018, the X Prize Foundation made it official. The Google Lunar X Prize would expire on March 31st of that year with no winner. Google had paid out in total exactly $0 of prize money. The foundation expressed gratitude to all the teams. They published a press release. They moved on to other things. At the time of writing, the X Prize Foundation is offering a $100 million prize for carbon removal, an $8 million prize for ocean exploration, and several others. The Lunar X Prize became formally a footnote. But here is the strange thing. The day the prize expired, 4 of the 5 finalist teams gave up. SpaceX did not. They had spent 8 years of their lives and $75 million chasing a prize that no longer existed. The head of the organization, the Israeli billionaire Morris Khan, looked at the situation in early 2018 and made an announcement that surprised almost everyone. They were going to finish the spacecraft anyway. They were going to fly it. They were going to try to land on the moon, without a prize, without the publicity machine of Google behind them, without, in a meaningful sense, any external reason to do it at all. When asked why, Khan said something that in retrospect ought to be inscribed on a plaque somewhere. He said, We started something and we need to finish it. That was the moment Beresheet stopped being a contest entry and started being something else. Something stranger. A national project. A piece of performance art. A $100 million argument that a small country with no national space agency to speak of could nevertheless do things that on paper only superpowers could do. But to understand how three young Israelis ended up making that argument and how it turned in the end into a 4-meter smear on the surface of another world, we need to go back even further. We need to go to a bar in Holon in the spring of 2010, and to a Facebook post that almost nobody saw. Yariv Bosch in late 2010 was 24 years old. He had recently finished a degree in computer and electronics engineering at the Interdisciplinary Center in Herzliya. He had served like most young Israelis of his generation in the Israeli Defense Forces, in his case in an elite intelligence unit. He had not yet started the company that would later become his main occupation, an Israeli drone delivery startup called Flytrex. He was by his own later admission looking for something to do. Bash had read about the Google Lunar X Prize. He had not stopped reading about it. He had been turning the idea over for months. What would it actually take in concrete terms for a small group of people working out of someone's apartment with no budget to speak of to put a spacecraft on the moon? The honest answer, of course, was more than they had. But Bash was not particularly interested in the honest answer. One night on Facebook, he posted a question to nobody in particular. The question was, who wants to go to the moon? 2 people responded. The first was Kafir Damari, who at 25 was also an electrical engineer, also a recent Ben Gurion University graduate, also recently demobilized from a cybersecurity-focused Army intelligence unit. He taught computer networking part-time. He was like Bash, restless. He responded to the post within a day. The second was Yonatan Weintraub, the same age, who had spent 2 years working as a satellite systems engineer at Israel Aerospace Industries, before leaving to pursue a PhD in biophysics at Stanford. Of the 3 founders, Weintraub was the only one who had actually worked on a spacecraft before. They met for drinks. It was depending on which of the 3 you ask, a bar in Holon or possibly Tel Aviv. The exact venue has acquired the slightly varnished quality that all founding myth venues acquire over time. What is not in dispute is what they talked about. Damari has said in interviews that the goal of the meeting was to see whether the project was in any way not insane, to see whether there was somewhere underneath the obvious objections a plausible path from where they were 3 guys with no money to where they wanted to go. The surface of the moon. Their initial estimate that night was that the entire project would cost $8 million and take 2 years. In the end, it cost 12.5 times that. And it took 9 years. This was their first lesson in spacecraft engineering. They did not yet know they were learning it. Nothing in space costs what you think it will cost. And nothing takes as long as you think it will take. Apollo ran 2.5 times over its initial cost estimate. The James Webb Space Telescope ran 20 times over. The European Space Agency's Schiaparelli lander, which we will return to in a later chapter, was about 3 times over budget by the time it hit Mars. The standard ratio in the industry is somewhere between 2 and 4. Space IL's final ratio was, if you do the arithmetic, 12.5. They were not particularly worse at estimating costs than anyone else. They were just starting from a smaller initial number. Within 6 weeks, the 3 founders had managed to raise the $50,000 required to officially register for the Google Lunar X Prize. The Israel Space Agency contributed. So did Israel Aerospace Industries, quietly in the form of unofficial technical support from Weintraub's former colleagues. They submitted preliminary blueprints, mostly aspirational sketches at this stage, just in time to make the deadline. They were now on paper in the competition. What happened next is a story that almost every space mission ever made has gone through, and that almost every space mission ever made has been unable to talk about with a straight face afterward. It is the story of the gap between the back-of-the-envelope sketch and the actual functioning spacecraft, the gap that for SpaceL would consume the next 8 years of their lives. They had no office. They worked out of a borrowed conference room at Bezalel Academy in Jerusalem. They had no money. They had no full-time employees, just the 3 of them plus a slowly growing constellation of volunteers. Mostly graduate students and engineers willing to donate evenings and weekends in exchange for the promise of being a small part of something historic. They had no spacecraft. They had a sketch. The first thing they needed was a sponsor with money. $8 million at minimum in their initial estimate. $20 million more likely in the early estimates from people who actually knew what it cost to build a satellite. They began in 2011 to make the rounds in Tel Aviv and Jerusalem, pitching their idea to anyone who would listen. Most people would not listen. The Israeli technology investment community in 2011 was not in the habit of writing checks for moonshots in the literal sense of the word. The standard pitch deck for an Israeli startup of that era was for an enterprise software company, or a cybersecurity firm, or a cloud storage outfit. Things that returned multiples in 5 years. The moon would not return any multiple at all. The moon would almost certainly return less than nothing. But there was one man, an aging South African-born Israeli businessman named Morris Kahn, who was prepared to listen. Morris Kahn was by 2011 somewhere in his early 80s. He had been born in Johannesburg in 1930, the son of Jewish immigrants from Eastern Europe. He had moved to Israel in 1956, 4 years before John F. Kennedy gave the speech that committed the United States to landing on the moon, and well before anyone had any sensible reason to believe such a thing was possible. In the decades since, he had built, sold, and invested in a long list of Israeli technology companies. He was a billionaire. He was also, by most accounts, a man with no particular interest in the conventional uses of wealth. When Bash Damari and Weintraub got their meeting with him sometime in 2011, they pitched him on the idea of an Israeli lunar lander. The pitch was not strictly speaking a good one. The team had no aerospace credentials beyond Weintraub's 2 years at IAI. They had no spacecraft. They had no clear path from a Facebook post to a functioning piece of hardware that could survive the trip to another world. What they had was a story. The story was that landing a spacecraft on the moon was the kind of thing only superpowers did, and that an Israeli spacecraft on the moon would be in a way the most powerful possible demonstration that Israel, a small country, a country less than a century old, a country with no national space agency to speak of in any serious budget sense, could nevertheless do superpower things. The secondary story was that this would, through some hard-to-quantify but hopefully real mechanism, inspire the next generation of Israeli schoolchildren to study science and engineering instead of becoming accountants. They called this the Apollo effect. They borrowed the name from a well-documented observation that in the years following the 1969 moon landing, applications to American engineering programs spiked sharply. Whether this mattered or whether it would happen again for a country that wasn't the United States was unknowable in 2011. But Kahn liked the pitch. Over the next 8 years, he would donate by various accounts somewhere between $27 and $43 million of his own money to SpaceIL. The total varies depending on which press release you read and which year. The point is, it was a lot of money, and it was the foundational layer of the funding that allowed Beresheet to exist at all. But $43 million is not enough to land on the moon. Not even close. Other donors would come slowly over the years. Miriam and Sheldon Adelson, the American casino magnates, gave a substantial sum. The Sussman family. Various others. The Israeli Space Agency contributed roughly $2 million over the life of the project, about 1% of the eventual total budget. This was the 10% government funding limit that the X-Prize rules had required, and SpaceIL ended up well under it. Beresheet was by any reasonable accounting a privately funded project, in a sector where privately funded projects of this scope had never existed before. The final budget in publicly stated terms was around $100 million. Different sources give slightly different numbers. Some say 90. Some say 100. The Israeli press during the launch window quoted 150 in some places. But 100 is the number most commonly cited, and it is approximately correct. Now, let us put $100 million in context. The Apollo program in 1960s dollars cost about $25 billion. In modern dollars, adjusted for inflation, that comes to roughly $280 billion. Beresheet's budget was, by that comparison, less than 1/2800th. That is about 0.035% of Apollo. Of course, Apollo also sent humans and brought them home and did it 6 times. The fair comparison is unmanned robotic landers. The Surveyor program, which preceded Apollo, sent 7 uncrewed robotic landers to the moon in the late 1960s. Adjusted for inflation, Surveyor cost roughly $1 billion per lander. Beresheet was 1/10 of one Surveyor. India's Chandrayaan-2 mission, which attempted to land on the moon a few months after Beresheet, cost about $150 million. Roughly 50% more, with substantially more government backing. China's Chang'e 3 lander, which actually succeeded in landing on the moon in 2013, cost an estimated $300 million. The Soviet Union's Luna series in 1960s dollars ran into the billions. Beresheet was not just cheap. Beresheet was by a meaningful margin the cheapest serious attempt at a lunar lander in the history of space exploration. By a factor of 3 at minimum. By a factor of 20, arguably. This was the constraint that defined everything that came afterward. Every design decision SpaceIL and II made, and we will spend the next chapter walking through them, was a decision made under the following pressure. We have 1/10 of the money everyone else gets, and we are trying to do the same thing they do. The way you cope with this constraint is ultimately by cutting things, by making compromises, by choosing components that have not been fully qualified for deep space. Because the components that have been fully qualified for deep space cost 10 or 20 or 50 times more than the ones that have only been qualified for low Earth orbit. By building fewer redundant systems than you would prefer. By writing software in RAM rather than burning it to flash memory. Because the deep space rated flash memory is too expensive and would extend the project timeline by another year that you cannot afford. Each of these compromises on its own was probably defensible. Each was probably the right call given the constraints. SpaceIL and II were not staffed by fools or careless people. They were staffed by smart, careful engineers who knew exactly what they were trading away. The problem with compromises as a class is that they do not fail linearly. They fail in chains. A spacecraft is a fundamentally interconnected system, and a decision to cut redundancy in one place sometimes propagates through the design in ways that are not visible at design review. You discover the propagation only when something else fails, usually for the first time. And the missing redundancy turns out to have been load-bearing. Beresheet was a $100 million compromise in 9 dimensions at once. It was small. It was light. It was fast to build. It used off-the-shelf parts where it could. It had only one onboard computer. It carried patches to its own software, only in RAM. It used inertial measurement units originally designed for low Earth orbit communication satellites, not for the radiation environment of deep space. It had no laser altimeter of the kind used by professional lunar landers. It relied on a much simpler set of optical and radar sensors. It carried only enough fuel for a single landing attempt, with no margin for an abort and retry. To put it another way, if any single one of these compromises had been the difference between success and failure, Beresheet would still be the cheapest lunar lander ever built. But the universe does not in general let you have things both ways. Let us describe the spacecraft itself in some detail, because most of what comes later depends on understanding exactly what it was. Beresheet as built was a boxy 4-legged structure, roughly 1.5 meters tall, and 2 meters across with its legs extended. Without the legs, it was approximately the size of a kitchen appliance. Hence the journalistic shorthand that became attached to it almost immediately. The spacecraft is about the size of a washing machine. This was technically accurate in the sense that the spacecraft's central body was about as tall and as wide as a typical front-loading washing machine. It was also somewhat misleading in the sense that a washing machine weighs perhaps 80 kilograms, and Beresheet fully fueled at launch weighed 585 kilograms. About the weight of a grand piano. Most of that weight was fuel, specifically 435 kilograms of bipropellant. About 74% of the launch mass. The fuel was monomethylhydrazine or MMH paired with an oxidizer called MON. MON is a mixture of nitrogen tetroxide and a few percent of nitric oxide. These two substances are hypergolic, which means they ignite the instant they touch each other. No spark plug, no igniter, no fancy combustion chamber preheating. You just open a valve and let the mix and combustion happens. This is a deeply convenient property for a spacecraft engine. Because it makes restarts trivial, you can shut the engine off and turn it back on as many times as you want in any environment with no ignition risk. Hypergolics are also extraordinarily toxic and require specialized handling on the ground, which is the reason most newer spacecraft use cleaner propellants when they can. Beresheet's designers, working on the small-budget tradition of the European satellite industry, chose hypergolics because they were reliable, well understood, and could be sourced and integrated cheaply. The main engine was a British-built unit called the Leros 2B, pronounced Leros 2B, made by a company called Namo at their facility in Westcott, England. The Leros family of engines has a long heritage in space. Variants of it have flown on NASA's near Shoemaker mission to asteroid Eros, on the Juno mission to Jupiter, and on dozens of communication satellites, but it had never before been used as a landing engine. It was designed for what engineers call apogee insertion maneuvers, the kind of single long steady burn you use to push a satellite from its initial elliptical transfer orbit into a stable circular orbit around Earth. It had not been designed for the kind of rapid throttling and stop-start operation that a lunar landing requires. Specifically, the Leros 2B could not throttle. It had one thrust setting 400 newtons, roughly the equivalent of holding up about 40 kilograms against Earth gravity. On the Moon, where gravity is 1/6 of Earth's 400 newtons of thrust, could comfortably support about 240 kilograms of spacecraft. As Beresheet burned through fuel during the descent, its mass dropped, and the engine became progressively more powerful relative to the spacecraft's weight. The flight computer compensated for this not by adjusting the throttle, it couldn't, but by pulsing the engine on and off in short bursts. Namo's engineers had been forced to modify the engine specifically to tolerate this stop-start abuse, which was, in the words of one of their lead propulsion engineers, the most stressful temperature environment the Leros had ever been asked to operate in. In addition to the main engine, Beresheet had 8 small attitude control thrusters, arranged around its body to allow it to rotate and make small translational adjustments. These were what aerospace engineers call reaction control system thrusters, or RCS. They were used for fine pointing during the cruise phase and for stability during the descent. They could not on their own slow Beresheet down meaningfully. They had nowhere near enough thrust for that. Their job was simply to keep the spacecraft pointed the right way, while the main engine did the heavy lifting. The body of the spacecraft was a rectangular structure made of aluminum honeycomb panels, wrapped in the now famous gold-colored thermal insulation foil that you see in nearly every photograph of the lander. This foil, called multi-layer insulation or MLI in the trade, has nothing to do with gold. It is a sandwich of metallized polyester film separated by mesh, and it is the standard way to passively manage temperature on small spacecraft. Beresheet had no active thermal control system, no radiators, no heat pumps, no fluid loops. It survived the trip to the Moon by passive radiation alone. On the lunar surface, where temperatures swing from 120 degrees Celsius in the sunlight down to -170 at night, this was expected to be a problem. The spacecraft was designed to operate on the surface for roughly 2 Earth days before overheating during the long lunar afternoon killed it. After that, it would simply die in place. 2 more things you need to know about the hardware, both of which will matter enormously in Chapter 10. First, Beresheet had 2 inertial measurement units, also called IMUs. These are small sensor packages about the size of a deck of cards, each containing accelerometers and gyroscopes that allow the spacecraft to know which way it is pointing and how fast it is moving without reference to any external observation. They are fundamentally the spacecraft's inner ear. The 2 units were redundant. Either one could provide full navigation data on its own, but they were not radiation hardened to deep space standards. They were a commercial-grade part originally designed for low Earth orbit satellites, which had never been characterized in detail beyond Earth's protective magnetosphere. This was a budget decision. Space-qualified IMUs, the kind flown on Mars landers, cost approximately 15 times what Beresheet's IMUs cost. Second, Beresheet had exactly 1 onboard computer. Not 1 primary plus 1 backup. 1. If it died or rebooted at the wrong moment or suffered any kind of failure, there was no second computer to fall back on. The reason again was budget. A second computer would have meant doubling the avionics cost and the testing burden and the integration complexity. Furthermore, the computer's working memory. Its RAM held all the software patches that had been uploaded during the mission to fix bugs discovered after launch. Those patches were not stored in permanent memory. They were not burned to flash. Every time the computer rebooted, those patches had to be re-uploaded from the ground. On top of these systems, Beresheet carried a small scientific package, a magnetometer to measure the moon's faint surface magnetic field, 6 cameras, and perhaps most strangely, a hockey puck-sized object called a lunar library. This was a project of an American futurist named Nova Spivak, who, along with several scientific collaborators, had encoded 30 million pages of human civilization onto 25 ultra-thin nickel discs, along with, and this is the part that became controversial after the crash, several thousand tardigrades in a dehydrated cryptobiotic state. Whether those tardigrades survived the impact is, as we will discuss in Chapter 11, a question that is probably best left unanswered for diplomatic reasons. This is the machine that they were going to send to the moon. Now we need to get it there. By February 21st, 2019, Beresheet was sitting on top of a SpaceX Falcon 9 rocket at Cape Canaveral Space Launch Complex 40, ready to fly. It had been a long road from the bar in Holon. The original 2012 launch target had slipped and slipped and slipped again. The Google deadline had come and gone. Most of the other Lunar X Prize teams had given up. Space IL had not. The mission had been delayed several times in the final weeks. The original target was December 2018, then January 2019, then February. There had been technical issues with the spacecraft itself, small software bugs, hardware integration problems. They had been resolved on a rolling basis. There had also been more frustratingly scheduling problems with the launch vehicle. Beresheet was not the primary payload of the Falcon 9. It was, in the language of the industry, a rideshare. A secondary payload sharing the rocket with 2 other satellites, an Indonesian communications satellite called Nusantara 1, and an experimental space situational awareness payload for the United States Air Force called S-5. Beresheet was in effect hitchhiking to the moon. This was in itself a first. No spacecraft had ever previously gone to the moon as a rideshare. The standard approach for lunar missions was to purchase a dedicated rocket, the entire payload of which was your spacecraft. This let you choose your trajectory. You went directly to a translunar injection orbit, the fuel-efficient ballistic path that gets you to the moon in about 3 days. Space IL could not afford a dedicated rocket. Instead, they bought a ride on a Falcon 9 whose primary mission was to deliver a communications satellite to geostationary transfer orbit, an elongated orbit that sweeps from low altitude out to about 36,000 kilometers above Earth. That was nowhere near the moon. The moon is about 384,000 kilometers from Earth on average. To get from geostationary transfer orbit to the moon, Beresheet would have to do all the rest of the work itself, using its own main engine. This was the heart of Space IL's clever budget trick. Instead of buying a direct trajectory, they used a series of phasing maneuvers, repeated firings of the main engine at the closest point of an elliptical orbit around Earth, that each progressively raised the far end of the orbit until it eventually reached the moon. The first burn lifted the apogee from 36,000 kilometers to about 70,000, the second to 140,000, the third to 270,000. The fourth pushed the orbit out past the moon's average distance. And on the 7th burn, a lunar gravity assist captured Beresheet into orbit around the moon itself. It is an elegant maneuver, in the way that elegant orbital mechanics are generally elegant. By trading a great deal of human patience for a modest savings in fuel, it is not, however, fast. The direct trajectory to the moon takes 3 days. Beresheet's looping phasing maneuvers would take 7 weeks. At 8:45 p.m. local time on February 21st, 2019, or in UTC, 1:45 a.m. on February 22nd, the Falcon 9 ignited its 9 Merlin engines and lifted off into the Florida night. The launch was by every measure a flawless one. The rocket performed nominally, The first stage separated and returned to land on a drone ship in the Atlantic. The second stage deployed each of its 3 payloads in sequence. Beresheet, the smallest payload, was the last to be released. About 33 minutes after launch, in mission control in Yehud, pronounced Yehud, the 3 founders embraced. Morris Khan on a live feed smiled in a way that he did not smile often. The first selfie Beresheet sent back a few hours later became one of the most shared images in Israeli media for weeks. The lander's gold foil-wrapped body in the foreground, a small Israeli flag plaque attached to its side, and the bright blue curve of Earth filling the background. On the plaque was inscribed in Hebrew and English the phrase, Am Yisrael Chai, which means, the people of Israel live. A few days later, the first phasing burn went off without incident. Beresheet was on its way to the moon. It would be, for the next 7 weeks, the smallest, cheapest, most ambitious spacecraft ever to attempt this particular journey. Nobody in those first days after launch was thinking very hard about the spacecraft's 2 IMUs. Nobody was thinking about the single onboard computer, or the patches that lived only in RAM, or the redundancy that had been cut for cost. Those decisions had been made and reviewed years ago. The hardware was performing nominally. The team in Yehud was ecstatic. This is generally the way space missions work. The hard part is launching, everyone says. The launch is the highest risk phase. Once you're in space, the rest is just, well, it's just careful operations. Routine. The systems are designed to work in space. They will work in space. Everyone says this. Most of the time in most missions they are correct. This was not going to be one of those times. In the weeks ahead, Beresheet would begin to surface a series of small alarming faults, none individually fatal, but each of them in retrospect a quiet warning about what was coming. The first of them appeared within hours of separation from the rocket. A star tracker on a spacecraft is exactly what it sounds like. It is a camera pointed away from any local light source that looks at the sky and compares what it sees to a preloaded catalog of star positions. By recognizing patterns of bright stars, the spacecraft can determine its orientation in space with remarkable precision, typically to within a few arcseconds of true. Star trackers are the gold standard attitude reference for any spacecraft that needs to point at something specific: a planet, an antenna on Earth, a target for a thruster burn. Beresheet had 2 star trackers, one on each side of the spacecraft. Within hours of separation from the Falcon 9, both of them began to behave strangely. They were intermittently blinded by what the team in Yehud could not immediately tell. The most likely culprit was sunlight, reflecting off some part of the spacecraft and entering the tracker's optical paths at an angle the designers had not anticipated. Star trackers are extremely sensitive instruments. The entire point of them is to detect faint pinpricks of starlight against a black background. Anything brighter than a star anywhere in their field of view can saturate the sensor and render the tracker temporarily useless. This was not a fatal problem. Beresheet had backup attitude references. Its 2 IMUs could maintain a navigation solution for an extended period without star tracker input by integrating gyroscope measurements over time. But the IMUs drift. Without periodic correction from a star tracker, the navigation solution slowly diverges from reality. The correction interval can extend from minutes to hours, to in extreme cases days. But eventually you need to look at the stars again. The team in Yehud spent weeks working around the star tracker issue. They adjusted Beresheet's attitude during cruise to keep sunlight out of the tracker's field of view as much as possible. They modified the timing of attitude updates as to make optimal use of the windows when the trackers were reporting valid data. They learned slowly to live with sensors that worked maybe 60% of the time. While they were doing this, the onboard computer began to reboot. The reboots were the more serious problem. Beresheet's computer was, as mentioned, a single point of failure. When it rebooted, the spacecraft was for a brief period uncontrolled, typically 2 to 5 seconds. The reaction control thrusters were inactive. The navigation system was not being updated. The communications link was dropped and had to be re-established. There were several causes for the reboots. Some were thermal. The computer would get too hot or too cold and trip into a protective mode. Some were the result of cosmic ray strikes, single event upsets where a high-energy particle from space would flip a bit in memory. and the computer's error correction logic would respond by restarting the affected subsystem. Some were caused by software bugs that the team discovered in flight and had to patch on the fly. This brings us to the most consequential design choice on the entire spacecraft. Beresheet software patches lived only in RAM. Random access memory. RAM is volatile. When the computer reboots, RAM is wiped. This meant that every time the computer rebooted, the carefully crafted patches that had been uploaded to fix in-flight bugs simply disappeared. The team in Yehud had to upload them again, every time, as a command file line by line over the radio link with the corresponding multi-second propagation delay between Earth and spacecraft. The reason the patches lived in ROM and not in flash memory was again budget. Updating flash memory on a flying spacecraft is a more complicated operation than updating RAM. It requires a more sophisticated bootloader. It requires careful management of memoryware leveling. It requires the kind of integration testing that takes time and money. Space IL did not have. So they chose the simpler implementation, with the known limitation that any in-flight patches would be ephemeral. This was a known limitation. The team had accepted it. They had practiced re-uploading patches in simulation. The expectation was that reboots would be rare events. In reality, reboots happened often enough during the cruise that the team in Yehud developed a kind of grim ritual around them. The computer would reset. The patches would vanish. The team would re-upload them. The spacecraft would resume normal operations. They would breathe out. They would go back to monitoring telemetry. A few hours or days later, another reboot. The same ritual. Each ritual was a quiet rehearsal for what was coming. Nobody at the time framed it that way. But every time the patches got re-uploaded successfully over a leisurely communications link with hours or even days to spare, the team was implicitly confirming to themselves that the system was recoverable. That reboots, while annoying, were not threatening, that you could always upload the patches again. This confidence was correct as long as you had time. During the cruise phase, time was plentiful. Beresheet was looping slowly around Earth, each orbit lasting days. Even a long sequence of reboots could be worked through methodically. There was no rush. During the landing burn, there would be no time at all. The team also worked throughout the cruise phase on what they called the mission rules. These were the pre-agreed responses to various fault scenarios. If X happens, do Y. If a star tracker fails, switch to IMU. Only navigation for up to Z minutes. If an RCS thruster shows anomalous behavior, isolate it and rebalance the control authority. And if one of the two IMUs trips offline during descent, what do? The mission rules as drafted called for the spacecraft to continue the descent on the surviving IMU. This was the correct answer from a safety standpoint. A single IMU was sufficient. Trying to bring the failed IMU back online during the descent burn was an elective action. It would restore redundancy, but it was not required for a successful landing. The mission rules were quite clear on this point. There was, however, a counter-argument that some members of the team held privately. The argument was, if you're already in trouble, you want the backup back. Continuing with a single IMU works as long as nothing else goes wrong. If the surviving IMU also fails, you have no navigation, and the spacecraft will crash. Restoring the failed IMU gives you a safety margin against that scenario. This argument is not on its face unreasonable. Redundancy, after all, is generally desirable. The mission rules answer to this counter-argument was yes. But the procedure for restoring a tripped IMU during descent has not been fully validated, and the act of restoring it introduces risks of its own. Stick to the plan. Single IMU. By the time Beresheet entered lunar orbit on April 4th, this debate had been had many times in many forms. The mission rules said single IMU. That was the agreed answer. That was the rehearsed procedure. What happened on April 11th in the 7 minutes between IMU-2's unexpected trip and the spacecraft's impact with the moon was not the mission rule answer. On April 4th, 2019, 6 weeks after launch, Beresheet completed the single most important maneuver of its mission to date. It fired its main engine for 6 minutes and 20 seconds, decelerating relative to the moon by about 470 meters per second, and slid into an elliptical orbit around the lunar body. The closest point of that orbit, the Beresheet, was about 500 kilometers above the lunar surface. The farthest point, the Beresheet, was about 10,000 kilometers out. If the burn had failed, if the engine had not ignited or had shut off early, or had pointed in the wrong direction, Beresheet would have sailed past the moon and continued into a heliocentric orbit, where it would have remained doing nothing of any consequence until it eventually fell into the sun some millennia hence. The burn was, in the strict sense of the term, make or break. It was conducted on the far side of the moon beyond direct radio contact with Earth. The team in Yehud had to wait until the spacecraft emerged from behind the moon to find out whether it had worked. It had worked. Beresheet was in orbit around the moon. This was the moment Israel became the 7th nation in history to put a spacecraft into lunar orbit. After the United States, the Soviet Union, Japan, China, India, and the European Space Agency. It was the first time a privately funded organization had achieved the same feat. By any reasonable measure, this was a substantial accomplishment in its own right. If Beresheet had failed in some catastrophic way on the very next maneuver, if its engine had blown up, if its computer had died permanently, if a meteoroid had punched through its tankage, Israel would still have been the 7th country to orbit the moon. Nobody on the team was satisfied with 7th. The goal had always been 4th. To put a spacecraft on the surface. Not just in orbit. Over the next week, Beresheet conducted a series of progressively tighter circularization burns. After the first lunar orbit insertion, the orbit was lowered on April 7th to about 470 kilometers. On April 8th to about 200. By April 10th, the spacecraft was in an almost circular orbit about 212 kilometers above the lunar surface, completing a full revolution every 2 hours. On April 10th in the evening, Israel time, Beresheet performed its final pre-landing maneuver. This was a small burn. 5 kilograms of propellant consumed. 32 seconds of engine firing. It lowered the Beresheet to about 15 kilometers above the surface. From this new elliptical orbit, with Apollon at 200 kilometers and Paraloon at 15, Beresheet would begin its final descent the next day, timed so that the spacecraft would arrive at Paraloon directly above the planned landing site. The landing site was in the northern part of Mare Serenitatis, pronounced Mare Serenitatis, the Sea of Serenity, one of the dark basaltic plains visible to the naked eye on the lunar surface. Mare Serenitatis is geologically an enormous ancient impact basin that filled with lava approximately 3.5 billion years ago, leaving the smooth, dark, relatively crater-poor surface that Beresheet's mission planners had chosen as a landing target. The specific site was unremarkable, a flat patch of basalt at roughly 33 degrees north latitude, 19 degrees east longitude. The landing zone was about 15 kilometers in diameter, which is to say a remarkably loose target. Beresheet did not have hazard avoidance. It would land where it landed within a roughly 200 square kilometer error ellipse, and hope it didn't land on top of a boulder. The night before the landing, Yariv Bosch recorded a brief video message for the SpaceIL Twitter account. He stood in front of a screen showing the spacecraft's current orbit. He was visibly tired. He had not slept much in the previous week. He explained in his calm engineer's voice what was going to happen the next day. The team would uplink the final commands. The spacecraft would orient itself for the descent burn. The Liros 2B engine would ignite. Beresheet would decelerate from orbital velocity, about 1,700 meters per second, about 3,800 miles per hour, sideways relative to the lunar surface, and over the course of 14 minutes slow to a controlled descent. At 5 meters above the surface, the main engine would shut off, and the spacecraft would free-fall the last few feet onto its 4 landing legs, which were designed with crushable aluminum honeycomb to absorb the impact. From engine ignition to touchdown, the entire sequence would take approximately 14 minutes. It would be entirely autonomous. The round-trip light delay between Earth and the Moon is about 2.5 seconds. Far too long to permit human reaction in real time. The ground team would watch the telemetry come in, and would not be able to intervene meaningfully if anything went wrong. "Everything has to work," Bash said in the video. "We have done everything we can to prepare. Tomorrow the spacecraft has to do its job." The next day was April 11th, 2019. In Yehud, the morning was clear and warm, early spring in Israel. The team gathered in the mission control room shortly after lunch. Morris Khan arrived in person, as did Benjamin Netanyahu, Israel's prime minister, who had chosen to watch the landing live with the team. The control room was crowded with engineers, journalists, photographers, and high-ranking officials from the Israeli Space Agency and IAI. There was a sense palpable to everyone in the room that something historic was about to happen. At 5:03 p.m. local time, the final commands were uplinked. Beresheet acknowledged them. The descent sequence began. The descent burn began at 1911 UTC. In Yehud, it was 9:11 in the evening. Beresheet was about 15 kilometers above the lunar surface, moving horizontally at approximately 1,700 meters per second relative to the ground. Its target was again a flat patch of Mare Serenitatis some hundreds of kilometers ahead along its ground track. The main engine ignited and began to fire continuously. The first time in the mission it had been asked to do a continuous burn longer than about 6 minutes. It would need to fire for nearly 14. The first phase of the descent went exactly as planned. The Liros 2B performed within its expected thrust envelope. The attitude control thrusters fired in small pulses to keep the spacecraft pointed correctly. Telemetry came in at high data rate, showing the spacecraft's velocity decreasing steadily. 1,600, 1,500, 1,400 meters per second, and its altitude decreasing more slowly. Since most of the spacecraft's velocity was horizontal, and the engine was working primarily against forward motion rather than altitude, the team in Yehud watched the numbers. Bash watched the numbers. Netanyahu off to the side watched the numbers. At 19:21 UTC, 10 minutes and 10 seconds into the burn, about 4 minutes from the planned touchdown, something happened. The specific event was in the moment almost unnoticeable on the main telemetry display. Down in the lower corner of one of the engineer's workstations, a small indicator flipped from green to amber. The amber indicator was the status of IMU-2. IMU-2 had stopped reporting data. It had not crashed in any catastrophic sense. It had simply tripped offline the way a circuit breaker trips when it detects a fault. The spacecraft's flight computer, as designed, automatically switched to IMU-1 for navigation. IMU-1 was working normally. The transition was clean. To a first approximation, nothing had gone wrong. This was exactly the redundancy scenario that the dual IMU architecture was designed for. The mission rules said continue on the surviving IMU. The mission rules had been clear about this for years. What happened in the next 90 seconds is in some sense the entire story of why Beresheet failed. It is the part of the story that the Space IL Internal Investigation Report, the one IAI's Space Division General Manager Ofer Duran has spoken about publicly, is most cautious about. Multiple senior engineers in mission control immediately suggested that the team attempt to recover IMU-2 by sending a reset command. The argument again was, get the redundancy back. Don't fly the rest of the descent on a single IMU when we have time to bring the other one back. There was disagreement. In the recordings of the mission control audio that have been released publicly, you can hear voices objecting to the reset decision. You can hear someone saying in Hebrew words to the effect of "don't do this." You can hear someone else saying, "We have the time, we have the time." It is impossible from the audio alone to identify the speakers with certainty. What you can hear is that the decision was not unanimous, and that it was made under pressure, and that the people who objected to it had reasons. The reset command was sent. Here is what nobody in the control room fully appreciated in the 15 seconds it took to debate and send that command. Beresheet's two IMUs, despite being labeled IMU-1 and IMU-2, and despite being nominally redundant, were not actually fully independent. They shared a common communications bus to the flight computer. The flight software had been written with the assumption that the IMUs were independent, that you could reset one without affecting the other. But the actual implementation at the software bus level did not behave that way. When the reset command was sent to IMU-2, the spacecraft's bus controller had to take the entire IMU communications channel offline for the duration of the reset, which was expected to be less than 1 second. During that less than 1 second, the flight computer received no acceleration data from either IMU. Not from IMU-2, which was rebooting, and not from IMU-1, which was online and working, but whose data could not reach the flight computer because the bus was busy. The flight software, when it detected the absence of acceleration data, did exactly what it had been programmed to do. It classified the absence as a navigation system fault, and the response to a navigation system fault hard-coded into the boot logic of the spacecraft computer itself was reboot the computer. So the computer rebooted. The main engine, which required continuous control commands from the flight computer to keep firing, lost its command stream. It shut off. It was now about 30 seconds after 1921 UTC. Beresheet was approximately 10 kilometers above the lunar surface. It was moving horizontally at over 1 kilometer per second. The main engine was off. When the spacecraft's flight computer rebooted, the boot process took approximately 2 seconds. By the end of those 2 seconds, the computer was back online. It had reloaded its baseline flight software from non-volatile memory. It had completed its self-tests. It was ready to resume control. Except, the flight computer, when it came back up, did not know what the spacecraft was supposed to be doing. The mission plan, the descent sequence, the engine throttle profile, the attitude commands had been loaded into RAM by the team during the cruise phase, and as part of the final pre-descent upload. None of that was in non-volatile memory. Worse, the software patches that the team had spent the entire 7-week cruise discovering and fixing, the workarounds for the star tracker glitches, the corrections to the descent timing, the various small refinements that had accumulated through the mission. All of those were also in RAM. All of them had just been wiped by the reboot. The flight computer, in effect, was a fresh installation. It needed the patches re-uploaded from Earth over the radio link. With the 2.5-second round-trip light delay, the team in Yehud uplinked the patches. The first attempt did not load successfully. The reason is not entirely clear from the public investigation summary. There may have been a corruption in the command file, or a timing problem with the upload protocol, or another small fault triggered by the rapid sequence of events. The computer rebooted again. The patches did not load. They tried again. The second attempt and also did not succeed. The computer rebooted again. In total, 5 reboots were required before the patches finally loaded successfully. The total elapsed time from the original IMU-2 trip to the successful patch upload was approximately 90 seconds. During those 90 seconds, Beresheet had been in essentially uncontrolled flight. The main engine was off. The reaction control thrusters were firing intermittently to keep the spacecraft from tumbling. But the RCS thrusters did not produce enough force to slow the spacecraft's descent in any meaningful way. At the moment the patches finally loaded somewhere around the 4th or 5th reboot, Beresheet was at an altitude of approximately 2 kilometers above the lunar surface, still moving horizontally at close to 1,000 meters per second, with significant vertical velocity now building up due to the lack of thrust against gravity. The team in Yehud had one chance left. Restart the main engine. They sent the command. The flight computer relayed it to the engine controller. The engine controller began the start sequence. And then it hit the second known bug in the spacecraft's design, a bug that the team had been aware of before launch, but had not had the time or the budget to fix. The Leros 2BA engine to start required voltage from 2 separate power buses. This was a safety design. A single power bus failure should not be able to cause an inadvertent engine start. But the team had discovered during ground testing that after a flight computer reboot, one of the 2 power buses did not reliably restore. To restart the engine, the team would need to send a separate command to manually re-energize the second bus before initiating the engine start. They had to send the command with the round-trip light delay. While the spacecraft fell, the team sent 5 or 6 commands to attempt to bring the second power bus online. Some of them, it appears, did not arrive cleanly because of the communications interruptions during the rapid computer reboots. Some of them arrived but did not produce the expected result. The spacecraft was by this point somewhere below 500 meters in altitude. The horizontal velocity was still close to 1 kilometer per second. The vertical velocity was building up rapidly. Eventually, and this is documented in the post-mission investigation, the main engine did restart, briefly, for perhaps a second or two. But by the moment of restart, the spacecraft was at an altitude of less than 200 meters. The engine produced 400 newtons of thrust. The spacecraft fully loaded had massed 585 kilograms at launch. By this point, after burning most of its propellant during the descent, it massed perhaps 250 kilograms. The thrust-to-weight ratio against lunar gravity was favorable. The engine in principle could decelerate the spacecraft, but the engine had 400 newtons. The spacecraft had nearly a kilometer per second of horizontal velocity to kill. Even at maximum thrust, the time to brake from 1,000 meters per second to zero would have been on the order of tens of seconds. Beresheet did not have tens of seconds. It had perhaps 3. The last useful telemetry packet from Beresheet was received in Yehud at 1923 UTC on April 11, 2019. The packet contained the following: altitude 149 meters, vertical velocity 134.3 meters per second downward, horizontal velocity 946.7 meters per second. That is approximately 3,400 kilometers per hour, roughly 2,100 miles per hour, approaching 3 times the speed of sound at Earth's sea level. On the surface of the moon, where there is no atmosphere, sound has no meaningful speed at all. But a kilometer per second is by any reasonable comparison fast. It is about 3 times the muzzle velocity of an ordinary handgun. It is about as fast as a high-velocity rifle round. In the next fraction of a second, Beresheet, moving almost horizontally, because nearly all of its remaining velocity was horizontal, struck the surface of Mare Serenitatis at an angle of approximately 8 degrees from the local horizontal. The angle is known from the geometry of the impact mark, which NASA's Lunar Reconnaissance Orbiter photographed 11 days later. There was no explosion in any Hollywood sense. Lunar regolith does not explode. What happened is closer to what happens when a hypersonic projectile strikes a sand dune at an oblique angle. The kinetic energy of the impact, perhaps 120 megajoules, roughly the energy released by detonating 28 kilograms of TNT, was absorbed by the fragmentation of the spacecraft. The disruption of the regolith and the lofting of about 150 cubic meters of fine lunar dust outward and downrange along the trajectory. The spacecraft was destroyed, not vaporized. The impact velocity was far below what's needed to vaporize the metal, but disassembled. Fragments of the lander were scattered along the impact trajectory for some hundreds of meters. The largest single fragment, presumed to be a piece of the central tankage, would later show up faintly in the LRO photographs as a small dark feature at the end of the smear. In Yehud, the telemetry stopped. The room went silent. Yariv Bosch, on the public live stream, kept his composure with admirable engineer's discipline. Ofer Doron of IAI, who had been watching from the side of the room, was visible on camera shaking his head once. Morris Kahn, the 88-year-old who had spent $43 million of his own money on this mission, leaned back in his chair and closed his eyes. The Israeli Space Agency posted the official statement to Twitter at 23:30 UTC. The statement read, "Beresheet's main engine failed. Spacecraft failed landing. Appeared to have crashed on the moon's surface." It was over. In the weeks that followed, Space IL and Israel Aerospace Industries conducted a joint internal investigation. The full report has not, as of this writing, been released publicly. What is publicly known comes from press briefings, from a detailed write-up by the Davidson Institute of Science Education in Israel, and from interviews given by senior IAI engineers, most notably Ofer Doron, the general manager of IAI's Space Division, who has been remarkably candid in his public statements. The investigation's findings can be summarized as follows. The proximate cause of the crash was a single command, the IMU-2 reset command sent during the final descent burn. The execution of that command triggered a cascade: the brief loss of acceleration data from the working IMU-1, the flight computer's reboot in response, the subsequent loss of the engine command stream, and the inability to restart the engine in time due to the previously known power bus issue. The investigation went on to identify the contributing causes. The proximate cause was, in a sense, the trigger, the event that on a properly designed spacecraft should have been recoverable. The contributing causes were the architectural decisions that made the trigger lethal, specifically the software bus design that conflated IMU-1 and IMU-2 communications contrary to the apparent intent of the dual EMU architecture, the flight software's hard-coded reboot response to a momentary loss of acceleration data, The decision to store in-flight software patches only in volatile memory, requiring a slow re-upload sequence after every reboot. The known power bus issue with engine restart, left unfixed before launch due to schedule and budget pressure. The use of inertial measurement units that had not been fully qualified for the lunar environment. And then underneath these technical findings, the investigation laid out the human element. The crew and mission control made a decision under time pressure, in conditions of high stress that was not in accordance with the mission rules. The rules said to fly the descent on the surviving IMU. The crew chose to attempt to recover the failed IMU. The rationale, as best it can be reconstructed, was that some senior engineers in the room believed the redundancy was important enough to take the additional risk of a reset. They were aware of the mission rules. They chose in the moment to deviate from them. It is worth being precise about this point. The investigation did not conclude that the crew made a wrong decision in the sense of malpractice or carelessness. They made a decision that on a properly designed spacecraft would have been recoverable. The decision became unrecoverable because of how the spacecraft had been built. If the IMU bus had been properly isolated, as it would have been on a more expensively engineered spacecraft, the reset command would have restored IMU-2 in less than a second, and the descent would have continued nominally. If the patches had been stored in non-volatile memory, the post-reboot recovery would have been faster. If the engine restart logic had not had the known 2-bus issue, the engine could have been brought back online earlier in the fall. The crash, in other words, was not the result of a single mistake. It was the result of a long, careful chain of small decisions, each of which was given the budget constraints defensible on its own, but which collectively eliminated the redundancy that should have allowed the spacecraft to survive its first real test. This is the pattern of nearly every space mission failure that the profession has studied in detail. Mars Climate Orbiter in 1999 was lost because one engineering team at Lockheed Martin used imperial units for thruster firing values, while the JPL navigation team interpreted them as metric, a unit conversion error that in any properly redundant testing regime should have been caught months before the spacecraft reached Mars. It wasn't caught because the standard review procedures had been streamlined to fit a tighter schedule. Mars Polar Lander also in 1999 was lost because a sensor in its landing legs was confused by the deployment of the legs themselves into thinking that the spacecraft had touched down, causing the engines to shut off prematurely while the spacecraft was still about 40 meters above the surface. The bug had been identified before launch, but had not been judged severe enough to warrant a software patch under schedule pressure. The European Space Agency's Schiaparelli lander in 2016 was lost because its inertial measurement unit saturated, that is, hit its maximum measurable value during the parachute deployment phase, and the flight software did not handle the saturated reading correctly. The software interpreted the spacecraft as already being below ground level and shut off its retro rockets at about 3 kilometers of altitude. Schiaparelli crashed at over 500 kilometers per hour. The Russian Luna 25 mission in 2023 was lost because of an incorrectly programmed orbital insertion burn. The spacecraft's main engine ran for 43 seconds longer than intended, leaving Luna 25 on a trajectory that intersected the lunar surface rather than the intended orbit. It crashed. The pattern across every one of these cases is the same. The proximate cause is some small specific failure, a unit conversion, a sensor misinterpretation, a software bug, a single misjudged command. The contributing causes are always architectural: missing redundancy, inadequate testing, schedule pressure, budget constraints. The narrative we tell about these missions in the years afterward often focuses on the proximate cause, because the proximate cause is dramatic and easy to understand. They confused metric and imperial. They forgot to handle a sensor edge case. But the proximate cause is rarely the real cause. The real cause is the chain of compromises that made the proximate cause unrecoverable. Beresheet's chain of compromises was longer than most, because Beresheet was cheaper than most. This is not a moral judgment. It is an engineering observation. You cannot land on the moon for $100 million and also have the redundancy budget of a $500 million mission. Something has to give. Space Isle made the decisions about what to give up, knowing the risks, accepting them as the cost of attempting something that was by every conventional measure financially impossible. Ofer Duran put it most clearly in a public interview some weeks after the crash. In an ordinary mission, he said, we would not have launched a spacecraft in such a condition. There was little redundancy of components and systems. Most of the parts were never tested in space. The likelihood of a successful lunar landing was very low, and we weren't sufficiently prepared. That sounds like an indictment. It is not quite. Doran was not saying that the team had been negligent. He was saying that to do what they did within the budget they had to accept a level of risk that no conventional mission would have accepted. They accepted it. They flew anyway. And they came within 149 meters. 2 days after the crash on April 13, 2019, Morris Khan made a brief announcement. Beresheet 2, he said, was beginning immediately. Space IL would build another lunar lander. They would try again. The announcement was in the moment mostly received as a gesture. The kind of thing you say when you have just lost something important and you cannot bear to admit that the loss is permanent. But Khan followed through. Within a few weeks, Space IL had laid out the preliminary design for a follow-on mission. By November 2019, the mission scope had been expanded. Beresheet 2 would now consist of 2 landers, with one going to the Moon and the other, and this part is not a typo, to Mars. The Mars component was eventually dropped, but the lunar component continued through several years of design work. In April 2025, 6 years after the original Beresheet crash, Space IL announced that it was suspending engineering work on Beresheet 2 due to funding shortfalls. The organization laid off approximately 25 employees and consultants. Supplier contracts were frozen. The project was, as of the most recent public reporting, an indefinite hold while Space IL sought new investors. Morris Khan turned 95 years old that year. It is not clear as of this writing whether Beresheet 2 will ever fly. Meanwhile, the wider commercial lunar landscape has changed dramatically. Beresheet's design was licensed to an American company called Firefly Aerospace, which used many of the technical lessons from the original mission to develop its own lunar lander called Blue Ghost. Blue Ghost successfully soft-landed on the Moon in March 2025, becoming by some measures the first fully successful commercial lunar landing in history. Other private companies have followed. The Japanese space company's Hakuto R mission, also a Lunar X Prize alumnus, has flown multiple landers. China and India have continued their state-funded lunar programs. The Artemis program is rebuilding American crewed lunar capability with extensive commercial participation. The era of national space agencies, as the only entities capable of landing on the Moon, is demonstrably over. Beresheet did not cause this transition. The transition was already underway when Space IL was founded, but Beresheet was in some meaningful sense the first concrete demonstration that a small, underfunded private organization could reach lunar orbit. The crash did not undo that. Israel had still become the 7th nation to orbit the Moon. Space IL had still become the first private organization to do so. The spacecraft had failed in its final 14 minutes, but the 12 weeks before that had been by any reasonable measure a stunning success. The Apollo effect, the supposed inspirational impact on a young generation, is harder to measure than mission success or failure. The data is by its nature soft. But here is what is known. In the months after the crash, surveys of Israeli schoolchildren showed that over 90% were aware of the Beresheet mission. School curricula across Israel had been built around the mission's trajectory and timing. The crash itself was watched live in classrooms throughout the country. Kafir Damari, one of the 3 founders, has said in interviews that in the days after the crash he was approached by parents and teachers who told him their children had cried. Not because they were upset by the failure, but because they had understood, perhaps for the first time, how hard it is to do something genuinely difficult, and how the failure of an attempt does not erase the attempt itself. This is, depending on your taste, either deeply moving or shamelessly sentimental. It does not ultimately matter whether you find it inspiring. It matters that for a small country with a small space program with 3 20-somethings at a bar and a Facebook post and a billionaire willing to listen, they had reached the Moon. They had reached it on the wrong terms, with the wrong velocity, in the wrong attitude, at the wrong angle. But they had reached it. The mark is still there. On the surface of the Moon at 32.6 degrees north latitude, 19.3 degrees east longitude, on the basaltic plain called Mare Serenitatis, there is an elongated white smear about 4 meters long, surrounded by a faint halo of disturbed dust, terminating in a small dark crater that is probably no more than a meter or two across. There is inside or near the wreckage a hockey puck-sized object containing 25 nickel discs etched with 30 million pages of human civilization and an unknown number of dehydrated tardigrades. There may or may not be. The science is genuinely uncertain on this. A small piece of Israeli law written into the regolith that says we were here. There will not be wind. There will not be rain. There will not be weather. The sun will rise and set in 2-week cycles for the next several billion years, and the temperature will swing from 120 Celsius to minus 170, and the slow drizzle of micrometeorites will eventually, on geological timescales, erase the smear and the crater and everything in them. But not soon. Not in your lifetime, or mine, or your grandchildren's, or theirs. For as long as anyone reading these words is alive, and for a very long time after that, the smear will remain. A small Israeli mark on the Moon. Not the one they wanted, but not nothing either. If you have been with this story to the end, thank you. The closing question, the one that the engineers in Yehud will probably argue about for the rest of their lives, is this: if on the night of April 11, 2019, the team in Mission Control had followed the mission rules, had accepted the loss of IMU-2, and continued the descent on IMU-1 alone, would Beresheet have landed? Would there be no smear on Mare Serenitatis today? Would Israel be the 4th nation on Earth instead of the 7th? And would the conversation about commercial lunar exploration look different than it does? We will never know for certain. But that, in the end, is the question the whole story turns on. Thanks for watching.